Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T, and I have a tutorial today on graphing exponential and logarithmic functions. In this unit, in the first lesson, we learned about applications using exponential growth and decay. And in the second unit, we learned a little bit about logarithmic functions and used them to solve exponential functions. So today we're going to be exploring those functions further by looking at their graphs. I'm going to be using Desmos here to have us explore the shape of the graph, and then we'll practice graphing some on our own. So I've graphed here in red the basic exponential growth and decay function. And let's explore what happens when we change the values of b. Now we know from our applications that when b was bigger than 1, it was exponential growth. So right now I have b equal to 2. Now if you look at the shape of this graph, when it's exponential growth, because b is greater than 1, on the left side of the graph, we're not actually touching the x-axis, it's getting closer and closer. If you remember from rational functions, we had something called horizontal and vertical asymptotes. So the exponential function has a horizontal asymptote of y equals 0. But unlike the exponential functions we looked at, it only approaches the asymptote on one side of the graph. For exponential growth, the function will approach 0 on the left side of the graph as x approaches negative infinity, and as we head to the right, the function gets larger and larger. And you can see this shape sometimes referred to as the hockey stick shape. So it rises gradually and then starts to increase rapidly. So if we change the value of b as we make it bigger, the sharper the hockey stick, and as we get closer and closer to 1, it close to levels out. Now when b is less than 1, now we have exponential decay. On exponential decay, it approaches infinity on the left side of the graph for negative values of x and approaches our horizontal asymptote on the right side. And again, as in this case, as b gets closer to 0, the hockey stick gets steeper. So let me put it back to growth. And then a, this multiplier in the front, if you remember from when we've done other things, the value of a as it increases, it's multiplying the function, so it's doing a vertical stretch. It's changing our y-intercept. And secondly, as a becomes negative, it flips the graph. Now this is still referred to as exponential growth because it's getting larger on the right side, even though we're getting to be larger negative numbers, so it maybe looks like it's decreasing. So this is still, because b is bigger than 1, exponential growth. When b is less than 1, so that it's decay, again the a value does the same thing. When it's positive, it's stretching vertically upward, and when it's negative, it's stretching vertically downward, causing a flip. So with that understanding of the graph, let's look at sketching some on our own. So this chart summarizes what we looked at in the previous graphs. So for exponential growth, b being greater than 1, as x approached negative infinity, so the left side of the graph, y approached 0, our horizontal asymptote. And when a was greater than 0 on the right side, as x approached positive infinity, y was going upward to positive infinity, and if a was negative, it was going downward to negative infinity. For exponential functions, our domain is all real numbers, meaning this function is defined for all possible values of x. When a is positive and its exponential growth, our range, the y values were all above the y-axis, so y was positive, and when a is negative, y will be less than 0, and our y-intercept is 0a. You can see a similar set of information for exponential decay. The main difference here is that the horizontal asymptote is when x approaches positive infinity, the right side of the graph. So let's practice a couple problems here. So we have two problems here. So we know here that we have, because of the b is greater than 1, we have growth. Now we know we have a horizontal asymptote at y equals 0. And since this is growth, we know that it's going to approach the horizontal asymptote on the left side of the graph. We also know that the y-intercept is at 0a, so in this case 0, 3. And let's just get one other point, so let's plug in x equals 1, and we would get now y equals 3 times 2 to the first, which is 6. So if we plot the point 1, this is 1 here, and 6 would be here, and then we can sketch in the exponential growth shape. This time b is less than 1, so we are decay. And our a is negative, so it's going to be flipped. So we're still going to have a y-intercept of y equals 0. And it's going to be, since a is negative, the graph is going to be y values of negative, and it's going to approach the intercept at, the horizontal asymptote on the right side because it's decay. Our y-intercept will be 0, negative 1.5. So right here. And again, we're going to plug in a value of x. For exponential decay, it's going to be better to pick a value of x equals to negative 1. So if we plug that in, we're going to have negative 1.5 times 0.5 to the negative 1, which is going to work out to be negative 3. You could use a calculator for that. So we have this point, and again, this is exponential decay, so it approaches on the right. And our domain for both of these, so the domain on this one is all real numbers, and our range for the problem on the left was y greater than 0, and on this one, our domain again was all real numbers, meaning we can plug any value in for x and have it be defined, and here y was always negative. Now we have another kind of exponential function, y equals e to the kt. Now we did that in the applications using continuously compounded interest. So our r here is now the k, and we're going to have our number in front to be 1. So I'm going to bring up the Desmos here so that we can look at the graph. So now we have y equals k to the x power. E, the natural number raised to kx. And let's look at what happens. So when k is a positive number, we have exponential growth. And the bigger the k value is, the steeper the hockey stick. And as k approaches 0, it starts to flatten out. For these functions, when k is negative, we have, you can see here, exponential decay. Since the number in front, where the a would be, is 1, on all of these examples, our y-intercept is at 0, 1. So let's go back to the notes. So again here, when k is positive, it's exponential growth, meaning our horizontal asymptote is on the left side. Our domain's all real numbers, the range is positive, and our y-intercept. When k is negative, we have exponential decay. So let's look at a couple examples. So we know here our k is negative, so we have decay. Again, our horizontal asymptote will be y equals 0. And it's going to approach, since it's decay, it's going to approach the horizontal asymptote on the right side. Our domain is all real numbers, and our range is y greater than 0. Now we can just make a table with a couple points. So if we put 0 and 1, let's make it negative 1 into a calculator and calculate the y. If we put 0 in, we have e to the 0 power. Anything to the 0 power is 1. And hold on a second, let me bring up a calculator. Okay, I've brought up my calculator and I put my -1 in for the x. And I get about 1.65, so we'll just round that to 1.6. So again, 0, 1 is our first point, and at -1, we're at 1.6. So about here. So here we have an exponential decay, and again, that's going to flatten out. We'll need to use a calculator and round because remember, e is an irrational number, and we're not going to get nice integers like we could get with the other functions. So this one's going to be growth. So let's put our horizontal asymptote. And for growth, we're going to get over here, our y-intercept will be 0, 1. So let's put in x equals 1. So y is going to be e to the 1.5. So if we calculate that here, second e to the 1.5, we get about 4.5. So at 1, we're at 4.5 right here. And we sketch our graph for exponential growth. Lastly here, we're going to look at logarithm functions. Now we haven't talked about inverse functions yet, but the log base b of x is a inverse of y equals b to the x. And when we study inverse functions are symmetrical around the line y equals x. So if I put the function y equals 2 to the x, exponential growth, graphed here in red, if I take any point on the graph here, so this is the point 0, 1, if I swap the x and the y coordinates, I get a point on the inverse function, which is the log function. So we can see here that the domain and range are reversed. So for log functions, the domain in this case is only x values that are positive, and the range, because it goes from positive to negative infinity, is all real numbers. So our domain and range are reversed. So let's bring up a graph of the Desmos and look at the graph. So I have the same graph that we looked at before. So in red is the exponential function, and in green is the log function. Darken these up so we can see it better. And we're going to change the base, and we can see that the exponential and log functions move together. And they look, when the base is a decimal, the log function flips over here. We're going to really be just dealing probably with log functions with bases greater than 1. And I plotted a point here, and we can see, so on red curve, the x is c and the y is b to the c. I reversed the x and the y coordinates on the to form a green point, and you can see that if I take any point on the red curve and I exchange the x and the y coordinates, we're following the green curve. So again, what we're interested in here is this is the shape of our log function. So let's graph a couple by hand. Now a minute ago I might have had this screen in a funny place. So again, I talked about this. So here we have our log function and the reverse. So for log functions, our domain, we can only take the log of positive x values. So the domain is x greater than 0, and our range will be all real numbers. And we know the basic shape, but we want to just pick some x values. So let's pick 0, 1, and I'm sorry, we're going to pick 0, we're going to pick 4, because I'm picking the b values here. So I'm going to pick b, and I'm going to pick 1 over b. So I'm going to pick 1/4. So to find the y, I've got the log, and I can't, my mistake here. We said the domain is greater than 0, so I can't pick 0. If I put that in a calculator, the log of 0 is undefined. So I apologize for that. I wanted to pick 1 here. So the log base 4 of 1 is 0. The log of any base of 1 is 0. The log base 4 of 4, remember our skill in the second exit ticket was to write this as into exponential form. Oops, I messed this up. Well, yes, I'm sorry, I didn't mess it up. So 4 to the what equals 4. So the question mark will be 1. So log base 4 of 4 is positive 1. And 4 to the what power equals 1/4. This is the reciprocal, so we get -1. Now remember, we could have also used the calculator to calculate these using the change of base formula. So we would take the log of 4 divided in this case by the log of 4, which would be 1. And we could have done the same thing here. So our points we have at 1/4, which is here, we're at -1. At 1, we're at 0. And out here at 4, we're up here at 1. And remember, this time we have, now that doesn't cross, that's not good. Let's see if we can draw that better. It's hard to draw a vertical line here on my tablet. So at here we were, point here. So we've got a vertical asymptote here on the y-axis. Oops, I missed. So let's see if we can kind of get this, try one more time here to get this to line up a little bit better. And that's going to keep increasing forever. So a little bit discombobulated here, but pick for your values of x when we are graphing a log function. We want to always pick the value 1 for x, the value of the base, and the reciprocal of the base. And if you pick those numbers, our answers here for y are going to be 0, 1, and -1. So if we plot those 3 points, we'll be able to get the shape of our logarithm function. Remember not to draw the function over here because the log function is not defined for values of x less than 0. If we put that in a calculator, we're going to get an error. So good luck with graphing your exponential and log functions, and I'll see you around.
Are you ready? Are you ready? Oh, are